Okay, it's 1:35, so I think we'll get started. And first off, I just want to poll the class members to see if there's any questions on the material, questions on the homework assignments that are due this week, anything that anyone's having problems with. I've had, some office hours and some individual questions, and people have put questions up on Canvas, but remember we are being recorded. That's just your reminder, but I'd be happy to field any questions now because, of course, the questions that you have about the class, other people are going to have as well, because we've got people here in synchronous lectures, and we also have a World Campus section. So we have colleagues that are tuning into the class asynchronously, but again, I'd be happy to answer any questions live here for anything that people want to talk about.
I have a question. Maybe it's gonna sound a little bit stupid, but I'm gonna go ahead. So
Sure.
is it possible for an amorphous polymer to become a semi-crystalline polymer, or the other way around, or no?
So that's a really good question. So semi-crystalline polymers have the ability to crystallize, but they don't have to crystallize. So a semi-crystalline polymer can be amorphous if it hasn't crystallized. And of course, a semi-crystalline polymer has amorphous fraction and crystal fraction. Now, an amorphous polymer that's known to be amorphous can never crystallize. And so something like atactic polystyrene is not able to crystallize because the chemical structure of polystyrene, of atactic polystyrene, can't form crystals. So that amorphous polymer can never become semi-crystalline. But if you take a semi-crystalline polymer and melt it all, it's amorphous. And so in general, when you look up a polymer, you should be looking for what's the TG, what's the chemical structure, what's the name, and then is the polymer known to be semi-crystalline or amorphous? Of course, if there's no TM and there's only a TG published, you can bet it's probably an amorphous polymer. But that's an important thing to think about in terms of once you identify a polymer and say, okay, this has the right properties I'm looking for, PET or PLA or whatever polymer it is, you should think about all those different facets of the polymer, what its thermal transitions are, whether it's semi-crystalline, amorphous, etc. And so that's really a good start for thinking about how to process a polymer in an additive manufacturing process. Because a lot of times people will buy a reel of material and say, okay, this is a recommended setup in my FDM process, I'm just going to use it. And they don't think about the material properties involved in that. And so the only way to think about new additive knowledge or new materials in additive manufacturing processes is to think about all these polymer fundamentals.
Okay, sounds good. Thank you.
Great, good question. Other questions, you can just chime in if you have anything you want to ask about, including syllabus, course notes, whatever is unclear to you at this point.
I had a question about the homework.
Yeah, go ahead.
So in the prompt, like you say that you want detailed descriptions of the polymer and you list like chemical structure, scientific name, molecular weight, etc. So in the paper, do you want like these specific details about the polymer, or should we cater it more towards kind of what our paper is about? Like for me, I'm looking more at like the electrical side of it, so I can detail like the loss tangent or the dielectric properties of the material instead of like molecular weight and more mechanical properties.
Oh yeah, yeah. So make sure you tailor the discussion of the polymer properties to the theme of the paper. I mean, it'll be good to know what the chemical structure is, because if you don't know what that is, it's hard to know what the polymer is. it's good to have an idea of, is this a high TG polymer, low TG polymer, semicrystalline, amorphous? So I would put in as much basic information as you can, and especially focus on information that you need to understand the theme of the paper. Like you said, if it's electrical properties, maybe molecular weight is not that important, but dielectric properties of that polymer, which is, another property of the polymer, are really useful. Is this a lossy polymer? Is this not a lossy polymer? What else is known about that? And the polarity or the chemical structure can give you an idea of the dielectric properties as well. So I would say that, make sure that you're adding some basic information to understand the material, but it should be tailored so it makes sense within your paper.
Okay, thanks.
But if you pick a paper and they say, we used Matter Hackers soft touch blue, we've got no idea what that is. And if Matter Hackers, which is a place where you buy filament, if they stop selling soft touch blue, we've got no hope of understanding what was in that paper. And so sometimes you'll have to dig a little bit because these filaments or whatever materials they're using, are not very well reported. And so you want to, at least for this assignment, look for the papers that have some kind of material detail. We'll have other assignments where design is more important, or some engineering property is more important, or the process is more important. But this one, since the first couple lectures have been about fundamentals of polymers, we want to make this first assignment, about fundamentals of the materials. Good question. Anything else people want to chat about? Okay, well, I'm available for office hours. I'm available for questions. And so we're finishing up lecture 1, and we'll get on to lecture 2, and we'll start to talk about 3D printing processes. But I wanted to just give you a couple more slides, especially on thermal properties of polymers, because we're going to set up 2 processes specifically that we're going to talk about thermal extrusion. One is material extrusion, AM, so MakerBot printing, etc., things that you're all familiar with. And the other will be powder bed fusion of polymer powder, where the same thermal properties are important, but there's a different reliance on viscosity, on feedstock, on things like that. And so you want to make sure that you keep in mind some of these basic polymer properties as we then talk about the thermal processing of these materials in future lectures. So this will all be relevant, and this is to warm you up to what polymers are and how they behave. Okay, so if there's no more questions, I'm going to share my slides. Well, I need to share my screen first. All right, I think you can all see that, and I'm looking at the chat window, so if you need to stop me or you just want to unmute yourselves, I think it's reasonable enough. We just have a few people on Zoom, so you can unmute yourself and chime in when you need to. Let me arrange everything here. So we left off on the slide before this one last time, and these diagrams can get complicated, or we talked about what happens with the volume change or the specific volume during crossing of the TM or the TG. And so we can boil this down to a diagram like this, is that there's really shrinkage due to freezing, or there's expansion due to heating. And this just isn't a polymer property. This happens for all kinds of materials. You know that when we crystallize water, ice has a 10% higher volume on a mass basis than water does. For other types of materials, crystals have a higher density than amorphous regions. So there's a shrinkage of volume when you crystallize. And so this happens in metals. This happens to some extent in ceramics. But this is important in polymers because of warpage, deformation, and built-in stresses during printing. So if we print isothermally, and isothermally means all at the same temperature, then there's no stress, no warp. But of course, that's very hard to accomplish because you need to heat the polymer in order to get it to flow or to get it the viscosity low enough, or you need to cool the polymer in order to solidify it. And so printing isothermally is not really possible, but there are lots of tricks out there in order to keep the thermal gradients as low as possible. And so why this matters for printing is we want to minimize thermal gradients and in that case we minimize thermal stresses because of this relationship. And so when we look at FDM machines, or we look at powder bed fusion machines, which are the two big thermal processes that we'll talk about, you'll notice that they're generally done in ovens. They're performed with temperature control. So not only do you have the hot part of the machine that's focused on processing the polymer, but there's auxiliary ovens or auxiliary heating in order to minimize these thermal gradients because of the CTE of the polymer and the shrinkage and expansion when we cross thermal transitions. And so that connects not only the transition temperatures, the temperature of TM and the temperature of TG, but it connects it to the volume change as well, which we need to keep a handle on. Okay. These are just some nomenclature, and this is to remind you that not all PEs are the same. There are lots of details. So you'll notice that when we read papers about polymers or we read papers about composites and additive, there's lots of these acronyms. There's lots of qualifiers. So this is all different types of polyethylene. There's at least 4 different types. And it's connected back to the synthesis route and the molecular structure of the polyethylene. But it helps to read the papers very closely. Is it PET or is it PETG? Those are 2 different types of polymers. Is it ABS or is it SIPS? Those are 2 different types of polymers. And so you'll have to look closely and think about how the nomenclature of the polymer or how the authors are describing the polymer relates to the polymer properties and the polymer industry, because all these polymers are generally made in big chemical plants. They're made for injection molding, and we just siphon off a little bit of this feedstock for additive manufacturing. The reason why we have lots of different grades of polymers is that we can span lots of different properties of polymers. So this is just one plot showing all different polyethylene. And so these are all different types of polyethylenes with different crystallinity. So when we look at this slide right here, we see a statement about crystallinity or percent crystallinity. This is out of 100%, how much of the material is crystal, and of course, the rest is amorphous. So for a polymer like HDPE, which is high density polyethylene, it has a high density for a polymer, and it has high percent crystallinity because crystals are more dense than amorphous, and crystals are stronger than amorphous. We know that crystals melt at higher temperature because Tm is always above Tg for the same polymer, but this plot shows that the yield strength goes up when the density goes up. And so higher density, oh, that's not density. Higher density equals higher percent crystallinity. And so this is why we make a lot of different variations of polymers. So you see that the yield strength varies by at least a factor of 2 in this plot, if not a factor of 2.5. And so that's just based on these small changes in density from 0.91 to 0.95 or so. And so this is to help you understand that all the different types of polymers out there are to give us all different types of mechanical properties and even different types of melt processing or different types of processing behavior. And we'll talk about different grades of polymers, which generally are there to give different processing characteristics. So for instance, we talked about this slide, if it comes up here. We talked about this slide last lecture. And so this is the effective molecular weight. And this looks like all the same polymer because it has the same modulus in the glassy region right here. It's got the same transition region and the same Tg. But in the rubbery plateau, you see that low molecular weight rolls off faster or rolls off at lower temperature than higher molecular weight. So as we change molecular weight, we change the viscosity or change the modulus as we heat these polymers up. And oftentimes different grades of the exact same material, different grades of HDPE will have different molecular weights, and then you get different viscosities because of that. And so when people buy a polymer for different properties, you know, oftentimes you can get the same modulus below Tg, but the viscosity, the melt flow index or the melt viscosity might be different depending on the grade. So they might make a high melt flow versus a low melt flow versus some other grade of material that's meant for injection molding or something else. And so that's important to remember as you look into these different polymers or you look up polymer properties on MATWeb. So this is one good website, www.matweb.com. There's tons of different materials in there, and oftentimes they talk about the different grades that are available. And that will become clear as we look in to more additive manufacturing grades of polymers. So this is just a reiteration of the slide I just showed you, looking at the rheology or the behavior of the polymer as a function of temperature when we compare semi-crystalline, this is not the perfect slide, versus amorphous polymers. So we know amorphous polymers only have a TG, and semicrystalline polymers have both a TG and a TM. And this shows now, if we say look at viscosity or modulus, we see that for semicrystalline polymers, we get a softening at TG, but it's relatively constant modulus between TM and TG, and then we get a drastic drop at TM. This will become important when we start processing semicrystalline polymers in FDM or in powder bed fusion. So we have to process semicrystalline polymers above TM. And in some cases, we only have to process semicrystalline polymers (20 to 30 degrees Celsius above TM, because the viscosity drop is so drastic at TM that we only need to go a little bit above TM before we get a viscosity that we can process. And by process, I mean do extrusion, do fused filament fabrication, fuse together polymer powders, etc. So by processing, I mean thermally shaping the polymer. But you notice for amorphous polymers like polystyrene, once we cross TG, the viscosity goes down, 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 and keeps going. There is no higher thermal transition other than, of course, T decomp, or the decomposition temperature. But in order to process an amorphous material, we might have to be 50 or even 100 degrees Celsius above TG to process. So this depends on the polymer. And so you really need to think about what is the polymer, what's known about its viscosity as a function of temperature. You really need this type of rheology plot or modulus versus temperature in order to design a processing scheme. But this gives you some ideas of what you look for when, if your boss comes up to you and says, I want to thermally process this polymer in material extrusion AM. Can you figure it out for me? And you say, well, do you have the rheology data on this? Or do you have the melt flow data on this? And so this type of plot from rheology sets you up to understand the modulus or viscosity versus temperature to figure out, A, where the thermal transitions are, but then figure out what is the characteristic viscosity that you need in order to process this polymer. We'll talk about viscosity ranges for different processes. Okay, are there any questions on this type of plot? And so when you look for papers, especially in thermal processes, the best additive papers for thermal processes have this type of data in it in some way. Are there any questions on what this might mean or how this might look in a real paper?
Dr. Hickner, I just had a quick question about temperature decomposition.
Go ahead.
Is there also a temperature decomposition for semicrystalline polymers?
Oh yes, for both of them. I mean, there's a TD for all materials, right? But for semicrystalline polymers and amorphous polymers, they both have decomposition temperatures. And it just really depends on the chemical structure, because when you're decomposing a polymer, that is reliant more on the chemical bonds within the system rather than any intermolecular forces or anything else. TG and TM are really driven by intermolecular forces, where decomposition is driven by the intramolecular interactions or the covalent bonds.
Okay, thank you.
Great. Okay, so beside the rheology data, of course, you have the DSC, and so you know about this. We've seen DSCs before, and this gives you the thermal transitions, but it doesn't say anything about viscosity. So you have a question for processing. What is viscosity versus temperature? And so DSC starts to help you, and you can use the rule of thumb that you probably want to start processing a semicrystalline polymer 20 or 30 degrees Celsius above TM, and you probably want to start processing an amorphous polymer about 50 or 100 degrees above TG. So this gives you a guess as to where to start, but you don't know anything about the viscosity, which you probably care about in a thermal process. And so this is only part of the story, but it's easier sometimes to get DSC data than it is to get rheology data. And so that's just a caveat, that if you can't find the rheology data, the DSC is a good place to start. There's also some things that have to do with the dynamic properties of polymers. And so when you're heating or cooling a polymer and you have high molecular weight versus short molecular weight, so short chains, of course, are low molecular weight. Long chains are high molecular weight. There's some dynamic properties that you have to be concerned with. So the apparent TG will change depending on molecular weight. Of course, we have this plot that we saw way back at the beginning dealing with the plateau molecular weight, but in a lot of cases, if we're looking for the glass transition temperature, we have a plot like this transition region, where for high molecular weight, we might have a higher viscosity polymer, and so the TG looks like it's at a little bit higher temperature than a low molecular weight polymer. Now that's a very subtle point, but when you're processing a polymer and you say, well, you know, it's not processing very well above its TG. I know this is PET. I know I should be able to process it at this temperature. Maybe you need to bump the temperature up a little bit for high molecular weight polymers versus low molecular weight polymers have a reasonable viscosity that you can process. So this is just something to remember. This plot is not perfect, but we'll talk a lot about this when we talk about shear rate. So this is describing polymer viscosity or polymer visco elasticity. So what this says is that as we decrease the strain rate, we have polymers that show a lower glass transition temperature versus if we increase the strain rate, so faster or higher strain, we get an apparent TG is higher. And this again, the glass transition temperature is really the apparent glass transition temperature, and it's due to the viscoelasticity of the polymer. And viscoelasticity means if we have high strain rate, or high shear, we get something that's more elastic or more rubbery. And so it resists the flow. And we'll talk about that because, of course, the harder you try and shear something, in some cases, the more it will resist being sheared. Versus at low strain rate, it will be more viscous, meaning it will be easier to shear at lower strain rate. And that shows up in this idea of the apparent TG. And so if you have higher shear rates, you're going to have to go to higher temperatures in order to get the polymer to shear as fast as, shear as high as you want, versus if you have a very slow process, and you can think of shear rate as the velocity or the speed of the polymer, which is related to the shear rate. If you have a very slow process, you might be able to go to lower temperature because you don't have to shear the polymers quickly. So we'll talk about that as we go on. And this is, again, just showing the different transition regions in terms of modulus versus temperature, and what might happen as you change molecular weight, what happens in what's called the rubbery plateau, and if you have a semi-crystalline polymer, what happens at TM. So that's just, again, giving you the idea of all these different transition regions and how you might use this rheology data to design polymer processing scheme. And in this case, the polymer processing scheme that we're going to worry about is fused filament fabrication or powder bed fusion. Of course, if I was teaching polymer processing, we would be talking about perhaps extrusion or injection molding or blow molding. And so this is exactly the data that industry has used to design those processes. We just need to use this same polymer behavior data to design and understand our additive process. Okay, any questions on those basic polymer behaviors, basic thermal transitions, the things about polymers that you have to understand to start to understand thermal additive? Okay, because we're going to start talking about polymers, and then I think we're going to get to lecture 2 that's going to start talking about additive. And so we're going to continue to build up the story, but these fundamentals you need to remember in order to understand how to use polymers and composites in additive processes. So this is a foundation that we build on. Oftentimes when you go and look up polymers, you'll see a chart like this. So this is the polymer type: polystyrene, polypropylene, and polylactide or polylactic acid. Every polymer has a glass transition temperature. Some polymers that are semi-crystalline have a TM. And so it's nice that they use TG and TM here. That's good. We can just go look these up. Polystyrene is amorphous. So it doesn't have a TM. So you'll read some papers sometime that talks about semi-crystalline polystyrene, or the crystals in polystyrene, or polystyrene crystallizes. And that's just not true unless it's syndiotactic polystyrene, which is a fancy variation of polystyrene that's not as common. Here's the percent crystallinity. That's great. And then this table is really nice because it tells you that what a qualitative idea of the crystallization rate. So polypropylene doesn't have any polar groups in the backbone, and it crystallizes very quickly. And so that means that you only, well, you can cool polypropylene quickly and it will crystallize to get the properties that you want, because strength comes from percent crystallinity. Where PLA has polar groups in the backbone, it's slower to crystallize. The percent crystallinity is still reasonable, but this will be a slower crystallizing polymer. And so you need to build that into your process, because in some cases, this rate will tell you how fast can you process or cool the material. And so as we get more familiar with the different additive processes, this will become more apparent. But this is a nice table. You see lots of tables like this, and now we can start to understand where these properties come from. Of course, polymers are awesome, but they come from places that look like this, which are not so awesome. And so we need to worry about where we're getting our polymer feedstocks from, and of course, what we do with polymers after we use them. And so we're going to talk a lot about commodity polymers, things like polystyrene, polyethylene, polypropylene, and this is where a lot of those polymers wind up, which is not good. So I think most people have experienced 3D printing, and you've probably experienced 3D printing through MakerBot printing of PLA, which is polylactide or polylactic acid. So there's no good reason that PLA has been the polymer of choice for starting 3D printing, other than its properties are just right for easy 3D printing. So it's a semi-crystalline polymer. It's got the right melt flow, and we'll talk about what that is in a second. It's got the right melt viscosity, and it comes in lots of colors, and it's non-toxic. And so it turns out that PLA was commercialized about 20 years ago, but other than some disposable cutlery and a few other compostable consumer items, they haven't been able to find any good uses of PLA. And so it just started to be used widely in 3D printing. MakerBot and others picked it up, and now we have lots of PLA filament. And this is the process, or this is why PLA is environmentally friendly, is it's made from a byproduct of sugarcane called lactide. So you take the sugarcane and ferment it, and you get lactic acid. And then from lactic acid, you can condense it and make PLA resin. So anytime you hear resin or people are talking about resins, that means some form of plastic or plastic precursor. You can recycle PLA. So if you've ever ground up a MakerBot part and remade filament out of it, you know that it's a thermoplastic. So you can grind it up, recycle it, remelt it, reshape it, do what you want. And then because it comes from sugarcane, or because it comes from this bio-based source, you can compost it. It doesn't break down very quickly, but it does eventually go back to CO2 plus water, which is the basic products of anything that's a hydrocarbon with a little bit of oxygen that you burn or decompose. Goes back to CO2 that the sugarcane can turn back into sugar. So PLA is a real success story in terms of bio-based plastics, but we don't make cars out of PLA. We don't make grocery bags out of PLA. We don't make lots of plastic things out of PLA because it's a little expensive and its properties are not as good as some of the other polymers we have. And so if you have the choice between using PLA and polyethylene, you're mostly always going to choose polyethylene because polyethylene is about 10 to 20 times cheaper. And polyethylene is also tougher, which means it can take impact and other things like that. PLA is a little bit brittle, and it turns out that making brittle consumer goods winds up, you make lots of broken plastic parts. And so you need that toughness or that ductility so you can drop your stapler or drop your mouse or your computer mouse on the floor and it doesn't break. Whereas if you had lots of plastic things made out of PLA, you would see lots of stuff snapping. So this is the story of PLA. This is its chemical structure. And so now you know what all those MakerBot filaments are made out of. PLA is called an aliphatic polyester because aliphatic means saturated carbons, and so that's what this has, and it's a polyester because this is an ester group. Does anyone know of any other polyesters? What are some other polyesters out there? Like when you buy a polyester shirt, what polyester is that? Has anyone heard of PET? So PET is an aromatic polyester. And PET, of course, is polyethylene terephthalate. It also is a thermoplastic, but since it's an aromatic polyester, it's not biodegradable. And it has a high TG and TM because aromatic groups increase the TG of polymers. And so PET, of course, is used for water bottles and all that stuff. And if you throw a water bottle in the ocean, it's not going away for a very long time. And just that small change between aliphatic units and aromatic units changes the polymer properties and the degradation completely. So that's important to remember. Okay. This is just a thermal map of what PLA looks like. So the references are given here. And so you can see that PLA has a glass transition temperature about in this range, a TM about in this range. Sometimes ranges are given, sometimes exact values are given. But you see that when we use PLA parts, generally they're brittle because we're using them at temperatures below 60 degrees Celsius. But we need to go up, in this case, plus 100 degrees C above TG, or 20 degrees plus 20 degrees C above TM in order to process this material. And so you can extrude PLA anywhere in the viscous liquid region. You don't want to get to the decomposition temperature. And so this is a good way to think about how you might use polymers or what the service temperature is. This is often called the service temperature. Versus where you might process the polymer into whatever shape you want. Any questions on PLA? Anything that people want to add about polylactide, their experience with polylactide, their experience with MakerBot printing, although we'll talk about that in the next set of slides. Any comments? Okay, like I said, PLA is often, you know, it's the reel of material or the reel of filament that you get with your first material extrusion AM printer. So this is the polymer that lots of people are familiar with. In your daily life, lots of people are familiar with this polymer. I think there's a lot of scientists and engineers out there in class, and so lots of scientists and engineers are familiar with Lego bricks. And if they're not familiar with Lego bricks, they're familiar with game consoles. And so even though this is a pretty old game console, all those telephones, like if you have a cordless phone or even mice, computer mice, or these old consoles, or probably even the PlayStation and Xbox nowadays are probably made out of ABS, because ABS is a tough consumer thermoplastic. It's a lot tougher than PLA. So if you make a part out of PLA and you make a part out of ABS, like Legos we know are indestructible, especially if you step on them, you know, they don't break. And so ABS is used for all sorts of plastic consumer goods, and it's used in automotive, plus composites. And so just talking about PLA, PET, which is a tough polyester, and ABS, we've covered a lot of the consumer plastics out there, aside from polyethylene and polypropylene, which are the most consumed plastics. But we don't additive a lot of polyethylene and polypropylene yet, because they're used a lot in cheap plastic stuff for injection molding. But ABS is an engineering thermoplastic. And it's a random copolymer of acrylonitrile, butadiene, styrene. So that's ASB or ABS, because that just has a nice ring to it, and it's in alphabetical order. And so these monomers give ABS its properties, along with molecular weight and all the other things that we've just talked about. And so ABS is a really useful polymer to get to know, and commercial grades, like I said, of ABS are sold. They're compounded to make composites, and we'll talk about compounding, but you see a lot of things made out of ABS. And it's also relatively inexpensive, because the monomers are relatively inexpensive. ABS is made like this. This is a really cool slide. If you've ever taken Professor Chung's MATSE 441 polymer synthesis course, you make a polybutadiene polymer first, and then you graft side chains onto that to get ABS. So this is styrene acrylonitrile side chains on a polybutadiene backbone. And of course, you can get cross-linking of polybutadiene, which you don't really want. But this is cool. Sometimes you see styrene acrylonitrile copolymers listed like this, or you see it as ABS. Of course, different companies call it different things. And so this is just something to think about in terms of, if you're interested in making polymers, this is how the big chemical companies make ABS, because acrylonitrile, butadiene, and styrene are all petrochemical byproducts. So all of these monomers come out of a refinery that look like this. So as you're making gasoline, you get a lot of other stuff out of there, and petrochemicals are part of the chemicals in petrochemical, and so that's where these monomers come from. And we'll talk a lot more about ABS, especially when it comes time for composites, because some cool stuff has been made out of ABS. So you see different properties here. We know what TG is. We know what TM here is. There's a recommendation in this reference of the printing temperature. We have the print bed temperature. For all of those out there that have done 3D printing, what does a heated print bed help you do? Does anyone have any input on why we talk about heated print beds?
Yeah, it has to do with several things. One is warpage. It'll lower your the overall speed of your isotherm as your part cools down, or at least help on the beginning of the print. And then second, it can also help with making sure your print stays, but lack of a better word, sticks to your print platform, adheres.
Perfect. Perfect. Yeah. So it helps adhesion because if the polymer is hot, it's a little bit stickier because you're near or above TG, and it especially lowers warpage. And so a heated print bed is required for some polymers because there's such a big volume change when they go through their thermal transitions. And of course, better than a heated print bed would be an oven. But not every 3D printer has an enclosed oven that comes with it, although we'll see examples of that. And so heated print beds do help lower warpage. They help your first few layers adhesion, and they're a substitute for not having an oven. Slumping temperature is interesting because you notice that the slumping temperature is just above glass transition temperature. And so you go through the TG, but the polymer is still pretty viscous. And then you get a little bit higher than TG and it starts to slump or it starts to deform. And of course, if we're making parts with shape, like we are with 3D printing, you don't want any slumping or deformation. So the thing that we haven't talked a lot about, and this is called a bunch of different things, but this is a nice part of this table, is the melt volume index. So what does the melt volume index mean? Does anyone know out there what the MVI is? Sometimes this is also called the melt flow index, or MFI, and we'll talk about that. But if you inspect the units, what do the units mean? Cubic centimeters per minute. What does this mean in terms of melt volume index?
It's how much polymer you extrude in a given amount of time. It's to do with the viscosity.
Perfect. So this is not a measure of viscosity because it's not units of viscosity, but it is a measure of how much polymer is extruded for a given time. So I think that was Benjamin, and he's exactly right that the PLA, you see, has a higher volume in 10 minutes. And so the PLA would be less viscous. So a less viscous material, you'll extrude more, versus ABS has a lower volume in 10 minutes. So ABS would be more viscous. What's missing is what temperature. Sometimes that's a standard, sometimes it's reported, sometimes it's for a given temperature above TM or TG. And so sometimes you have to dig for what temperature the MVI or the MFI is taken at. Sometimes it's reported, but it's a way to help you understand how easily the polymer flows without making a viscosity measurement. And so lots of times you'll see MFI reported or MVI reported instead of viscosity because it's a standard measurement that the polymer industry is interested in. So good. Taking a look at the units will often tell you exactly what the quantity is. Any questions so far? Anything people want to bring up? You can just type it in the chat, or you can just unmute yourself. Either way, whatever works for you. And so, again, chime in if you have questions, but this is the last slide in lecture 1 is, remember what polymers are, these long strings, and especially polymers are viscoelastic. And this viscoelasticity will really come into play when we talk about thermal properties. Of course, all the thermal transitions are dependent on what the polymer are. So just like we choose different polymers for different applications, all of those different polymers will have different thermal transitions, different processing requirements, different viscosities. They're semi-crystalline or amorphous. They'll have different molecular weights. And so this lecture is really setting us up to understand polymer and composite additive manufacturing from a materials point of view. Now, we're going to transition away from materials for a little while and talk about additive processes, but we're going to go back and forth between processes in materials, because the whole point of this class is to bring the understanding of those two things together. And so in your homework, if you're more interested in 3D printing machines and part design, you can focus on that. If you're more interested in materials and polymer chemistry, you can focus on that. And so, again, if you're interested in other topics, you can put that in the discussion group on Canvas. But this really sets a stage now for us understanding how to connect things like the monomer and chemical structure and some of the current uses of materials to how we're going to use them in additive. So any questions, any comments before we move on to lecture 2 here? Okay, I'm not hearing anything out there in Zoom land. We have, let's see, 20 minutes to go. So we'll give a start on lecture 2. And so again, you can find all these lecture slides in Box. They're annotated in real time. That's what my iPad is doing when it's thinking, is it's saving it to Box in real time. And so you can download the slides so you have some blank slides to write on, and then you can go back and look what I've written if you can decipher my writing. And if you can't make out what I was writing as you're watching the video and I'm writing here, just go ahead and ask me, say, your writing's not clear, what does it say on the slide? There's no problem revisiting that. Okay, so we're going to talk about these processes. So this in general is thermal material extrusion, AM. Sometimes you see it abbreviated material extrusion, AM. That's the ASTM nomenclature. Of course, thermal is on there. So we're talking about thermoplastics, because we can deform all of these polymers with heat. And this is, in general, the domain of extrusion, molding, injection molding, blow molding, rotomolding, etc. There's a huge industry. In fact, probably 80% or 85% of the plastic junk out there is made using some extrusion / molding based process. This is how plastic parts are made. And this is how plastic parts are made by the tens of millions in all industries. And so we're going to take those lessons of thermoplastic processing and all the stuff that we just talked about in lecture 1, and we're going to talk about how that's used in thermal material extrusion AM. So in order to think about this process, let's think about some of the machines, because of course we can identify with additive manufacturing because we can walk up to a machine and we can take a look at it. So this is not like blow molding or injection molding where there's just a few of those machines on campus. There's 3D printers everywhere. These are some of the commercial ones from companies like Stratasys. And so there's lots of different variations of these. Even you can buy one of these types of thermal material extrusion AM printers for $100 on Amazon. And I know some of you have these sitting on your desks at home. This is an industrial scale material extrusion AM machine. And you notice it's got an oven. And you also notice that it has lots of parts. And this is a Fortis 900 MC from Stratasys. And this black polymer is probably some kind of composite. They don't say exactly what it is in this picture, but if you go to Stratasys' website and click on some of these printers, you can click on the materials that are available for these printers. So whether you're interested in Ultem or ABS or PLA or some other thermoplastic. Stratasys has a menu of materials that they've certified that are compatible with their machine. So again, the oven is there to limit warping. And there are lots of parts that are built in this, and so you can get dozens of parts out of one build. And this technician is taking these parts out and getting it ready for the next step. So that's cool. And there's a lot of these types of printers around. This is a state-of-the-art industrial material extrusion AM. And there are bigger material extrusion AM printers than this that we'll talk about near the end of this lecture. Of course, there's lots of MakerBots around. You can go to the library. If you've never had a 3D printed part of your own, you can order one from the Maker Commons. That's part of your student fee that you pay. They're still open, even with the way campus is now. Or if you're interested in looking at some of these, you're welcome to arrange a tour of my lab. Of course, tours will be hard to pull off, but we'll do our best in terms of showing you around. But there's lots of cool YouTube videos. There's lots of cool stuff out there in terms of even what simple MakerBots are capable of. And this has been a real revolution because, you know, I was around when PCs came into existence and desktop publishing was a big thing. You could print out typed pages from your computer, which was amazing in the 1980s. Now you can print out three-dimensional objects from your computer, which is really amazing, just like you could print out two-dimensional pages 30 years ago. So this is cool. And there's lots of inspirational videos out there about MakerBots. I suggest you check them out as you're doing your YouTube research some night. Ultimaker is a nice brand name, and this gives us an idea of now what's inside these printers. So these are our material extrusion nozzles. And you notice that there's two in this Ultimaker. And we'll talk about the breakdown of these machines and why we're using nozzles. But these nozzles are on the order of 200 microns to, let's say, 500 micron orifice. And this defines the road, or defines the filament, or defines the string of polymer that we're going to build the part out of. So this is a heated nozzle. And of course, we bring in the filament. So this is a filament feedstock. And we'll talk about other feedstocks for material extrusion AM. But Ultimakers are a lot like MakerBots. It's just a different company. They're able to do different things. But this starts to give you an idea of what this process looks like, especially if you haven't been up close and personal with one of these types of printers. TAS printers from Aleph Objects is another type of printer. So you can see all the components here. So this is a real filament. And so that needs to be made in the first place. So you need an extrusion process to make the filament. The filament in this picture is cut off, or it's on the back of the machine. So this is fed into the extrusion nozzle here, and there's a motor right here that controls the filament feed. So if you're interested in machine design, if you're interested in control of these printers, or how these printers work from like an electrical, mechanical type of perspective, we're not going to teach a lot of printer fundamentals in terms of controls and details of the mechanical system. We'll talk a lot about the fundamentals of what happens at the nozzle and how the printing process impacts the material. But there's other classes at Penn State or other things that you can do to pick up ideas about the mechanical system of the printer, including the hobbyist community and the internet community is all over these things. People interested in building their own printers, people building printers in Africa from e-waste. There's a lot of cool stuff out there in terms of the hobbyist community and really digging into new printer technology or how these printers work from a nuts and bolts perspective. We won't focus on that here, but if you're interested in that, just get in touch, or I can help you do some of your own research. We talked a little bit about dual filaments. So anytime we say dual filaments, this is now different materials. In the same build. And so we'll define a build as a part or component. You know, the thing that we're going to make. And so with the dual filament, and this is just showing two different colors, but this could be hard and soft materials that are integrated together. I'll show you a slide that has water soluble and water insoluble materials integrated together. There's lots of things that you can think about with this simple material extrusion thermal process. Now, as you introduce dual materials, you don't get things that are boring pieces of one color plastic. You can start to imagine things that are interesting and useful. And we'll talk about some of the advantages and disadvantages of this type of printing, but it can get sophisticated. And there are industrial parts that are made using material extrusion AM because there are these huge industrial printers that are built, are sold. And so we'll see a really cool example of people making car fenders with material extrusion AM. So there's industrial uses of this. Of course, I'm showing you some hobbyist pictures just to get you warmed up about the possibilities, but this is a type of thermal processing that's used in industry today to make test parts and to make parts that go in engineering systems. So we can't ignore thermal material extrusion AM just because a lot of us are familiar with it through MakerBots. There's a lot of serious things going on. These are just,
I have a question about the dual filament. Yeah. So you're saying they can also be different materials, or does it need to be the same? Like, can they be completely different polymers?
They can be different polymers. They can have different temperatures. Each of these nozzles can be at a different temperature. You know, they basically, the way the machine works is that they trade off extruding. You know, one nozzle is working and one nozzle is resting versus the other nozzle is working and the other nozzle is resting. And so if you Google or on YouTube, if you look at dual material extrusion or dual filament printing, there will be lots of examples of how these printers work in terms of depositing different materials at different times. And the printing software plays a role here. So we won't talk a lot about the software that's needed to control the printers. That's taught in the other AMD courses. But the software, when you design an object in CAD, you assign different parts of the three-dimensional object, different materials in essence, and the 3D printing software knows what material to print when. So multi-material printing, or in this case, dual material printing, there's a lot of things that have to happen, but the idea of using different materials and integrating them into one component is really useful to make stuff that's not just boring single pieces of plastic like this.
So I guess what you're saying is that each nozzle will have like the correct temperature, the correct, I don't know, like dispensing velocity for the appropriate material that's used, right?
That's right. It's basically like two different printers, but they work together, and that's all integrated by the software.
Okay, thank you.
Good. So these are just some more examples, just for show and tell. But again, there's lots of cool stuff out there on YouTube. And so we won't stare at lots of YouTube videos in this class, although I do have some very cool ones. So this is just something to think about. And one of those cool materials or one of those cool videos is here. Let's see if I can grab this. Oh, maybe I can't. Let's see if the link is still live. Oh, see if I can switch things here. There we go. Oh, I'm not going to be able to get it. Well, my Zoom is not loving that video. I should have queued it up before. I apologize for that. But I'll show this video when we start off next time. But I suggest you check out this link right here. What this object is this is a PVA support. And this is white. And inside this PVA support, this is probably an ABS object, which is gray. And this is really interesting. So this is printed as one object. And so, of course, in 3D printing, you all know that this thing is printed layer by layer. On an Ultimaker, but it's printed, each layer has different materials within it. And so because PVA is water soluble, you can take this whole object, immerse it in water, and then it reveals the gray object. And again, we'll start off with this video if I can get it queued up and working on Zoom next time. But this is a real powerful demonstration of what you can do, and it was printed on this simple Ultimaker printer. So we have two nozzles. We have one for the material we want, one for the PVA support, and you can make something that's just impossible to make using traditional polymer processing through injection molding or some other process. So oftentimes when you look at a plastic part, like I'm holding my auxiliary cell phone battery in front of me, I can see a seam around the plastic part where the two halves were glued together. Or if you look at your remote control, it separates into two halves. And that's because in injection molding, you can't make a closed cavity very easily because of the way injection molding works. But with 3D printing, you can make lattices, you can make closed cavities, you can make shapes that you just can't make using another polymer processing technique. And that's one of the things that we'll talk about in future lectures in terms of decreasing part count or increasing complexity. That's one of the reasons why the plastics industry is interested in 3D printing versus all the types of polymer processing that we do now. So anyway, this is a cool video. I suggest you check it out. It's pretty awesome. And I'll show it next time, just to remind you if I remember. So there is lots of information out there on, in this case, they call it FDM, but we know FDM is also called FFF, and in ASTM nomenclature, it's called material extrusion, AM. And there's some really nice knowledge base articles and case studies out there to give you an idea of what's going on in these different printing processes. And so one of the most important things that we have to remember for FDM is this idea of minimum feature sizes. So if you look very closely at this part, or if you look closely at this part, or this part, you can see the stripes as the layers. So as we're building up layer by layer, first layer, second layer, third layer, fourth layer, fifth layer, etc., because the nozzle has a specific diameter between, let's say, even 100 microns to 500 microns, that leads to very specific dimensional requirements in the part. So now the process, the nozzle size, is connected to what the part looks like or the resolution in the part. And that's because it's really hard to extrude a polymer out of a nozzle that's smaller than, say, 100 microns or 0.1 millimeters. And so we'll talk a lot about these characteristic dimensions and how they're matched to the process, whether it's powder bed fusion and the size of the powder really impacts what your resolution is, or whether it's stereolithography that uses liquids, or polyjet that uses liquids, and so we have a different resolution. But now we can sort of connect our understanding of the process and the process parameters to what the part starts to look like, and it mentions it here. And so this is where we'll stop for today. If you have questions, you can chime in now or put something in the chat. But now we start to think about, okay, we know about polymers. We can't extrude polymers through a teeny little orifice. And so we're going to have a specific nozzle size, and that's going to lead to shapes in the part that we need to worry about in terms of resolution and tolerance. And we'll continue building up this story. We'll continue talking about material extrusion AM for a little while and talk about the polymer processing variables that go into understanding thermal material extrusion AM of thermoplastics. And both thermoplastic polymers and thermoplastic composites, which are polymers with some filler in it. So whatever we understand about polymers, we can apply to composite materials as well. Any questions? Okay, I will see you on Zoom on Thursday. Please remember your homework, and please be in touch if you want to chat. Thank you very much.
Thank you.
Thank you.
Thank you.